A very good morning and welcome back to the course Microwave Engineering, 7th semester B Electronics and Telecommunication course. So as discussed in our earlier lecture, today we are going to start with the understanding the theory and principle of impedance matching. In earlier lecture, we understood the necessity of making use of an impedance matching circuit. If you recall back, in earlier lecture, we considered three different cases in which we dealt with three different types of impedances: a generator impedance, a characteristic impedance of a transmission line, and finally a load impedance. Now, when these impedances are not equal with each other, then what happens? It's going to give rise to reflected waves, either at the generator end or at the load end or at the both. So whenever the reflection takes place from any of these particular end, we call that mismatch is occurred. In order to come over to this particular problem of mismatch, we already saw that what the mismatch is going to bring. Okay, so the mismatch is going to reduce the amount of transfer of power from the generator to the load. Okay, so the main purpose of designing the matching circuit is to remove or to circumvent the effect of reflected wave, so that maximum amount of power will get transferred from the generator to the load via the given transmission line, right? So impedance matching network, there is a different variety of designing the impedance. First of all, we will see a simple method to match the given real value of an impedance with a transmission line. Now the scenario we already discussed, the quarter wave transformer, and here today in this particular lecture we will be starting with developing a theory to match a simple real valued impedance to a given transmission line with certain characteristic impedance, right? So we will come across that. So here if you observe quarter wave transformer technique, I will zoom it so that we can visualize it. So the first method that we are going to discuss is the quarter wave transformer. Now the quarter wave transformer is a useful and very practical circuit for making use of impedance matching. So the quarter wave transformer, so we'll see that what is quarter wave transformer in a soon time. So this particular circuit is used to provide impedance matching for real valued impedances, please remember. So, and it also provides a simple transmission line circuit. So this particular matching circuit is very simple as it is made up of a simple piece of a transmission line. Okay. Now let us see what this quarter wave transformer or this matching circuit look like. See here the figure over here. Now what we have over here is on the left hand side over here. If you visualize my pointer over here, I am indicating on the left hand side over here. On the left hand side over here, there is a generator. Now this generator is connected to a load impedance. Now the load impedance is on the right hand side over here, right? Now here we observe clearly that the load impedance is a real value which is indicated with RL. Please remember that this quarter wave transformer technique is only utilized when we want to match the real value of given impedance, right? So this impedance is only having the real value, that is resistor, load resistor. Now this resistor we want to match to a transmission line. So this is a transmission line. The characteristic impedance of this transmission line is Z0, right? And on the left hand side of a transmission line, there will be a generator. Now please remember that in the design of quarter wave transformer or this matching circuit, it is already assumed that the generator side on the left hand side of the transmission line is already matched. And our aim is to design the quarter wave transformer such that the load impedance on the right hand side of the transmission line will get matched into the characteristic impedance of the transmission line on the left, right? So here if you visualize over here, now I will highlight the region, okay, let's say, so, or otherwise I will show with some color, right? Now this particular section, right? So here, over here. So whatever the rectangle selection here I'm showing, so this rectangle section contains a quarter wave transformer piece of a line. Okay, so if you visualize over here clearly inside this blue rectangle, so whatever portion of the transmission line is there, this portion of the transmission line is acting as a transformer, and the length of the transmission line is lambda by 4, or it is a quarter wave. So that's why the name is given quarter wave transformer technique. So what is a quarter wave transformer matching circuit? A quarter wave transformer matching circuit is a piece of a transmission line which is inserted in between generator side and load side, such that its length is always odd multiple of lambda by 4, or quarter wave. Okay. Now here our aim is to make use of this additional lambda by 4 circuit in order to match the given load impedance with the characteristic impedance of a transmission line. Okay. So here I will denote with different color. I will pick up. Let's say I will choose this yellow color, not yellow color. So this, okay. So this load resistance. So I highlighted the load resistor with a circle. Now this load resistor is having only real value. Now this I want to match with a characteristic impedance over here. So the characteristic impedance over here is Z0. So here the aim of using this quarter wave transformer circuit is to make equal the load resistance value to the characteristic impedance of a transmission line by inserting a lambda by 4 piece of a transmission line. Okay. So here as shown in the figure, the following circuit indicates the quarter wave transformer. The load resistance is indicated with RL, and the feed line or the transmission line characteristic impedance is Z0 over here, right? So here please remember that the load impedance here, it is a RL, it has to be real, okay, and Z0 is also a real value, okay. So these two components are connected with a lossless piece of a transmission line. So this transmission line has a length of lambda by 4, and this transmission line is itself known as quarter wave transformer. Okay. So here we are making use of lambda by 4 piece of a transmission line. Now what is the job of this transmission line? The job of this transmission line is to make this reflection coefficient on the main transmission line to become 0. Please remember that this quarter wave transformer matching transmission line, when it is used for matching load resistor RL with a characteristic impedance Z0, there are not going to be any reflection on the main transmission line on this side. But please remember, there could be possibility of occurrence of standing wave ratio on the quarter wave transformer itself. Okay. So what we are doing, we are suppressing the reflected wave which will take place at the generator side over here. Okay. So later on in this particular lecture, we will see a brief tutorial on understanding of the concept of voltage standing wave ratio and the reflection coefficient. Okay. So let us go further. So here our aim is very simple over here. Our aim is to match this resistor, load resistor RL, with a given characteristic impedance of a transmission line, that is Z0, using a piece of a transmission line whose length is a lambda by 4, and we want to calculate the characteristic impedance of that lambda by 4 transformer. We know, or we have given the values of characteristic impedance of this transmission line. The load impedance we know. Now we are interested to calculate what should be the value of impedance of this quarter wave transformer. Okay. So here we will develop that theory of designing a quarter wave transformer. Now here we already know from the theory of transmission line that the input impedance, see here in the diagram, the input impedance calculated by looking into the quarter wave transformer towards the load side, it can be given with this particular equation. Okay, so here I will denote or I will highlight. This is the equation. Okay, so here Z in, the input impedance that is obtained by looking into the quarter wave transformer toward the side of a load is given by Z1 times, where Z1 is the impedance of the quarter wave transformer transmission line. RL plus JZ1 tan beta L divided by Z1 plus J times RL tan beta L. Okay. So beta is 2 pi by lambda, and the L is the length of that quarter wave transformer. We already know that the quarter wave transformer has a length of lambda by 4. So when we substitute beta L 2 pi by lambda into lambda by 4, the total phase shift we will get pi by 2 radians, right? So what we do for this particular equation, the numerator and denominator we divide with tan beta L, and then we take the limit as beta L tend to pi by 2. Okay, so when you divide the numerator and denominator by a factor tan beta L, and when we take the limit as beta L tends to pi by 2, so what we will get? We will get the input impedance equation simplified as Z in is equal to Z1 square divided by Rn. So earlier Z in was given with this equation, and when we divide the numerator and denominator by tan beta L, and when we take the limit, beta L tends to become pi by 2, that is a 90 degree, then we will get the input impedance, the same input impedance, Z in is equal to Z1 square upon L. So it is very easy. You can have your manual calculation over here. You divide the numerator and denominator only by tan beta L, and you take the limit as tan beta L is equal to pi by 2. In that particular case, the cot beta L term will become infinity, and this equation of input impedance will simply reduce to this simple. That is Z in is equal to Z1 square divided by RL. So here our aim is to make gamma, that is a reflection coefficient at the main transmission line, to be 0. Okay. So in order to make gamma is equal to 0, we know that the Z1 value should match to Z0 value. Okay. So here the same thing is given over here, that is the input impedance, that is Z in, should match to Z0. Okay. So the input impedance, whatever the wave that will look into the transformer, it should be Z0. So here in this particular equation over here, see again I will highlight this particular equation. So what we do is here in this particular equation we substitute Z in is equal to Z0. Okay, then we will get the equation in terms of Z1 is equal to, see this is an important equation, Z1 is equal to square root of Z0 into RL. So what is Z1? Z1 is the impedance of the quarter wave transformer. So the impedance of the quarter wave transformer, mathematically it is given by equation 3.86. What it indicates? That the impedance of the quarter wave transformer is simple a geometrical mean of the characteristic impedance of the transmission line and the load impedance with which we want to match it. So it is square root of Z0 into RL, right? So when we substitute a transmission line of length lambda by 4, please remember lambda by 4, how to calculate lambda by 4? We should know first the operating frequency of this quarter wave transformer matching. Say, please always remember the generator is operating at certain microwave frequency. So that microwave frequency is going to decide what is the value of lambda. Okay, so that lambda has to be known to us. So lambda by 4 means we need to take the length of transmission line equal to lambda by 4. And here we calculated this value of Z1. So how the Z1 value is given? Simply it is given as square root of product of characteristic impedance of a transmission line multiplied by the given value of real load impedance. Okay, so here it is given in equation 3.86. So with this particular value of impedance, if we take a transmission line of length lambda by 4 at a given operating frequency, we will ensure that gamma is going to become 0 and there will not be any reflected waves on the main transmission line. But please remember that this particular arrangement, though it ensures that reflection is going to be 0 on the main transmission line, but there could be possibility of having the standing wave ratio on the quarter wave transformer itself, right? So therefore, the standing wave ratio on the main transmission line will be 0 and we will get the standing wave ratio as we discussed already. When gamma becomes 0, we will get standing wave ratio is equal to 1. But please remember here the same mention is over here, although there will be a standing waves at lambda by 4 matching section. Now please remember this condition will get only applied when we keep the length of the transmission line always lambda by 4 or odd multiple of lambda by 4. So how to give the odd multiple of lambda by 4? Odd multiple is given by 2n plus 1 times of lambda by 4, where you can keep the value of small n 0 to any value, and always you will evaluate this multiplication as an odd multiple of lambda by 4, so that a perfect matching will be achieved at one only particular frequency. Now please remember that whatever matching that we are going to achieve with respect to this load impedance and the characteristic impedance of a transmission line using a quarter wave transformer, it is only applicable for a single frequency range, but it is not at all applicable for the different range or the different frequencies. Okay, so the same is stated over here. The perfect match is only achieved at one particular frequency, but when we change the operation frequency, the mismatch will occur at other frequencies. Okay, say the limitation of this particular matching technique is it is limited to only real values of load impedances only. So this particular method is useful when we want to match the load impedance such that when the load impedance is only real value. Okay, so if it is a impedance is the complex value, okay, so that means it will contain the real part as well as imaginary part, certain reactance. So at that time this method is not that much of efficient, though the imaginary impedance can be made real by inserting a piece of a transmission line. So additional process of inserting a piece of a transmission line we need to perform whenever we want to match the complex load impedance matching using a quarter wave transformer. Or otherwise, on the other hand, when we have only the real value of load impedance, it won't be a difficult issue for us to make use of this quarter wave transformer technique, right? So here we saw the basic underlying theory. What do we mean by quarter wave transformer matching and why it is used? And we also saw what are the limitations of this quarter wave transformer technique, right? So the main and only disadvantage of this particular quarter wave technique is it is normally utilized whenever the given value of load impedance is only having a real value. Okay, but on the other hand, if the given value of load impedance is a complex, then still we can make use of a quarter wave transformer technique, but in that case we need to make certain modification. So in that particular case, first of all, we need to convert the complex given load impedance into real impedance by inserting a piece of a transmission line. So as on when we come across a typical example, it will be clear to you how to go for the designing of impedance matching circuit using quarter wave transformer technique. Okay, and the impedance of the quarter wave transformer, it is given as simply the square root of product of characteristic impedance of the transmission line with the given value of real value of load impedance, right? So the limitation of this quarter wave transformer is only it is limited to real values of load impedance only, and it is only applicable for single frequency operation. On the other hand, at the other time when we change the frequency of operation of the generator over here, the matching will not be provided by the same transformer. Okay, so please remember, so this is the another limitation of a quarter wave transformer. The quarter wave transformers are best suitable whenever we are going to keep the operating frequency fixed and a single frequency. It is not applicable to provide a matching condition for different values of frequency of operation, right? So, so this is the foundation theory which we just developed for understanding the use of quarter wave transformer. Okay, and we already discussed the generator and load mismatches in our previous lecture. And now let us go ahead and see what do we mean by lumped element matching. Okay, lumped element matching or impedance matching. Okay, so lumped element matching is one of the technique, although in this particular lecture later on we will see one more video tutorial in which lumped element matching, one particular short video will be demonstrated to you people. Okay, so let us go ahead with other different methods of impedance matching. Please remember, we already discussed a quarter wave transformer technique. Okay, so there are again certain more methods are available for providing us the impedance matching. Now, a general way to represent impedance matching circuit is shown in this figure 10. Okay, so if you visualize over here, what we have over here on the left hand side is a transmission line having the characteristic impedance Z0. Okay, and this transmission line on the left hand side, though it is not shown over here, it is assumed to be present over here, that is a generator. So the generator is always assumed to be present on my left hand side. Okay, so this generator is matched with the given load impedance having the value ZL. Okay, now this matching of the load impedance with a transmission line of characteristic impedance Z0 is achieved by inserting a network in between the transmission line and the load impedance. This particular network we call it the matching network. Now this network you can design with a different varieties. As the first method we already discussed, you can include here the quarter wave transformer, or there are different other methods of providing the impedance matching that we are going to see in a less time. That is, the first one is the lumped element matching. So here, as shown in the figure, the basic idea of impedance matching is to insert a matching network. So this matching network is ideally assumed to be a lossless, and it avoids the loss of a power. Now this impedance matching network is inserted between the transmission line, which is connected to the source on the left hand side, and between the load. Okay, such that the impedance when it is seen by looking into the impedance of matching network is Z0. Hence, the reflections are eliminated on the left hand side of the matching network. Please remember, the job of the matching network is to provide matching such that the reflection on the left hand side of the matching network are avoided. But however, it may be possible that the reflections are taking place on the right hand side of the matching network. Okay, our aim is to provide zero reflection on the left hand side of the matching network, right? Hence, the reflections are eliminated on the left hand side of the matching network. This procedure of matching the impedance is also known with the other name as impedance tuning, or simply as a tuning. As long as the load impedance, say this ZL value, is non-zero value, and if it is having a real part, then there always exists a matching circuit. Okay, so as far as the given load impedance has the real non-zero value of load impedance, there is always a solution to find a matching network. Okay, so here the impedance matching or tuning is important. So there are certain reasons why the impedance matching or impedance tuning is important for us. Now the reasons are described over here. See, what is the reason to provide or to make use of a impedance matching or a tuning network is the maximum power will get delivered when the load is matched to the line. Please remember. Okay, so the thing is that whenever we provide impedance matching, please remember at that time we will ensure that the maximum power will get delivered from the source to the load. The second reason to make use of a impedance matching circuit is the impedance matching sensitive receiving component. Sensitive receiver components like antennas, low noise amplifier. If we make use of a impedance matching circuit, please remember these sensitive devices. The example is antenna at the receiver side, the low noise amplifier. they can improve signal to noise ratio in a wireless communication system. So if we provide a best matching circuit, the receiver side sensitive devices like antennas and low noise amplifiers, they are going to provide us best signal to noise ratio in a wireless communication and signal processing. Okay. So impedance matching is also useful as a power distribution network, which is used in antenna array feed network, which will reduce the amplitude and phase error. So these are the main reason why we should go and we should design an impedance matching network for the given microwave circuit. Okay, so these are the main three reasons that we discussed. What is the need for designing an impedance matching circuit, although it is already discussed in our earlier lecture. Now let us go ahead with the second method of impedance matching. The second method of impedance matching is the impedance matching using lumped element technique. Now we will come to across that particular video of what do we mean by lumped element and distributed element, and we will see that within no time. But let me explain you here what do we mean by lump types. Okay, so lumped element matching is the simplest type of impedance matching network which is available for the analysis of transmission line. So here lumped element matching circuit are in the form of capital letter English letter L. So that's why they are sometimes also known as a L section networks. Okay. So what this L section network contains? This L section network contains two reactive elements which are used to match the arbitrary given value of load impedance to the characteristic impedance of the transmission line. Okay. So here if you observe carefully this diagram over below over here in figure 11, there are two diagrams. Let us discuss the first diagram first. So here where we observe the L-type circuit, the L-type circuit I am highlighting over here. So this is that particular matching circuit. And similarly in the second figure, the L-type matching circuit is over here. Okay. So the name is itself indicating as the reactive elements are arranged in English capital letter L like configuration. These type of matching circuits are known as lumped or L type matching circuit. Now please remember what is the common thing in between these two networks. There is a load impedance, complex load impedance on the right hand side. Now this complex load impedance we want to match with a characteristic impedance of a transmission line. So that can be done by inserting a L network, and this network will consist of a series arm. So please remember the series arm is denoted with this element. So this is a series element, right? Okay. So here the series element is over here, right? And there is another element called as a shunt element or parallel element. So this parallel element I will take some different color, parallel element. So this parallel element is over here. So this is a parallel element which I shown with a different color. Okay. So what is the L section network? The L section network is just a combination of reactances. The reactances are arranged such that there is a one reactance in series arm, which I indicated over here with the first circle for these two cases, and there is another reactance in the parallel arm, which I indicated with this second circle for these cases. Okay, so there are two configurations available over here. Now which configuration to use at what time, so that will be clear to you right now, just that we will be going to it. So there are two possible configurations as we discussed for this matching network. So which configuration is used at what time? So that is going to depend upon what type of load impedance it is. So in order to make the decision which type of L matching section we will use for our given example, that depends upon what type of load impedance is. Now, how to find the type of load impedance? First of all, we need to normalize this load impedance. Normalizing the load impedance means dividing the given load impedance with the characteristic impedance of a transmission line. Okay, and plot that normalized value of load impedance into the Smith chart. Okay, so when we plot that point normalized impedance point into the Smith chart, and if that point is lying within inside 1 plus jx circle. We'll come to this part later on when we come across that simulation tool of Smith chart. Now 1 plus jx circle, we normally call it as a unit resistance circle. So simple the methodology over here to decide which type of configuration one can go for designing. See, here the two configurations are there. See, when we begin with load impedance, the first element is a parallel over here and the second element is series. So this is one configuration. The second configuration is when we start from the load impedance, the first element is a series. Here the first element was parallel. Here the first element is series. The second element is parallel. Earlier, the second element was series. So these are the two different configurations. So which configuration is used at what time, that depends on whether the given normalized value of load impedance is lying within unit resistance circle or outside unit resistance circle. Now please make sure that when we find that the normalized load impedance is going to lie within a unit resistance circle or 1 plus jx circle, then we are going to make use of this host configuration, in which the first element have to be a parallel element and the second element have to be a series element. On the other hand, if we find that the load impedance, normalized load impedance, is not lying within unit resistance circle, if it is lying outside of it, at that time we will make use of the second configuration. Okay, so we'll quickly come to that particular point, what is unit resistance circle and how to plot the impedance point and how to determine whether one can go for choosing this particular circuit or this particular circuit for designing the impedance. Okay, so let us go ahead and complete our discussion first, the theory part, and then we will see a simulation software, and then later on we will go into the watching of a particular video in order to make our concept clear. Okay, so for just time being, you just remember that there are two different configuration of L section matching network available. The L section matching network, the name is given because the arrangement of the matching element is done in the English capital letter L like configuration. So that's why the name. And there are two possible configurations are available. Which configuration to use, it depends on whether the normalized value of given load impedance is lying within unit resistance circle or not. Okay, so we go ahead. In either of the above configuration, the reactive element, so please remember here jx stands for inductive reactance. Okay, so jx, whenever we take the x, the reactance, x stands for reactance. Okay, and whenever x is in series arm, it will indicate inductive reactance, right? And there is another imaginary part called as a JB. Now where B is called as a susceptance. Susceptance is a reciprocal of reactance, please remember. Okay, and JB stands for capacitive reactance normally when it is used in a parallel configuration. So here the reactants are arranged in either a series and the susceptances are arranged in the parallel configuration. So whenever we add a reactive element in a parallel, we deal with a susceptance, that is B, and whenever we add the imaginary part, the reactance, in a series, okay, so whenever we add the element in series, it will be treated as a reactance. Okay, in the above configuration, the reactive elements will be either inductor or capacitor. Okay, so there are only two different ways to provide you the reactive element. So these reactive elements could be either representing inductor or capacitor. It depends on what is the type of a load impedance. So hence there are total 8 possible configurations. Okay, so here if you make, say there are two different reactive elements available for us. One is a inductor and another is a capacitor. So inductor capacitor, how many combinations you can make in this particular diagram for the first configuration? So here you will get inductor inductor, capacitor capacitor, inductor capacitor, or capacitor inductor. So here you will get a 4 combinations. Likewise here also you will get a 4 combination. So for these two configuration, in total we will get 8 different types of the circuit networks which are constructed using inductor and capacitor. Okay. So if the frequency is low and if the circuit size is small, see, please remember, this is a very important discussion over here. Okay, so this is, see here, I will highlight it. If the frequency is low enough and if the circuit size is small enough, the actual lumped element capacitor and inductors are used. This may be feasible for frequencies up to 1 gigahertz or so. Okay, so this is a very important statement. If we are operating the given microwave circuit at a low frequency up to 1 gigahertz or so, then it is very much advised for us to make use of discrete values of capacitor and inductor for the construction of matching circuit. Okay. On the other hand, if we are dealing with a very high frequency and the circuit size where the lumped elements may not be realizable, at that time the impedance matching circuit using L section cannot be utilized. So the solution for that particular case is one can go for designing a stub element rather than lumped element. So that we will see in a later part. Okay. So here we saw that by using a lumped element components, that is inductor and capacitor, arranged in English capital letter L like configuration, we can design L section matching network. So please remember over here that we can place either the inductor in series or in parallel, and similarly we can place the capacitor in series or the capacitor also in parallel. So how we are going to place the inductor and capacitor? Okay. So based on it, we need to have an equation in order to evaluate the series values and parallel values of inductors and capacitor. So next what we will discuss is the standard empirical equations in order to find out the values of inductors and capacitor when they are used in series and in parallel configuration, right? So we will come across that standard equation table of element. So here if you observe, carefully observe, and I request you people to jot it down quickly because these formulae we are going to require whenever we solve and when we design the impedance matching network using lumped element using inductor and capacitor. At that time we need to find the particular values of inductor and capacitor, and that time we do need this design equation. Okay, so for just time being, you don't just pay attention to what do you mean by the nomenclature over here, you just jot it down quickly. So this concept I will make you clear in within a short time by taking the example demonstration of Smith chart using the simulator tool, right? So here the inductor, when we want to use in a series, what is the formula to calculate the value of series inductor? Use this particular formula. Okay, so J omega L is equal to J times into bracket reactance at destination minus reactance at source multiplied by Z0. Now just for time being, you don't pay attention to what do you mean by destination and source. So these are the selection points. So the meaning of this destination point and source point will be clear to you when we actually go for the example, right? So I request you people to just quickly jot down all these four important formulae to calculate the different values of capacitor and inductor in different configuration. Similarly, capacitor, when it is used in series, use this formula. When you want to make use of parallel inductor, use this formula. And whenever we want to make use of parallel capacitor, then make use of this particular formula. Okay, so what do you mean by reactance? What do you mean by susceptance? Okay, what are the sign conventions that we need to take in order to consider the values? That now we are going to make clear. Okay, so quickly take down this particular table. This table we are going to refer every time whenever we are going to design the impedance matching circuit using lumped element using a Smith chart. Okay. So I hope that you people have jotted down this particular empirical equation table to calculate the lumped values of inductor and capacitor in different configuration.